this Theoretical Thursday is to determine the wavelength of light that is emitted from this laser, and to do that we are going to put one of these diffraction gratings in front of the light emitted from the laser, and from there we are going to measure the nodes that are diffracted using this diffraction grating.
So we know the distance between the laser and the board is 1 meter. We can measure the distance between these two nodes, and the angle is measured, the angle to the node is measured by using arctangent of the opposite over adjacent. And through using that data, we can find the wavelength of the laser.
Alright, so as you can see from the diffraction grating, we have two nodes diffracted from the laser, but there should be more nodes. Why can't we see the other ones? Alright, so we had to turn the lights off because we couldn't see the other nodes with the lights on. So as you can see, there's the primary node and then the two other nodes, but there are more down, all the way down on the other end. Don't know if you can see that. All the way down there is the other node, and then all the way on the other end is the other node.
Now, some of you may be wondering, what is an actual laser? Well, it's actually an acronym that's spelled for Light Amplification by Stimulated Emission of Radiation.
Now, most of you probably know what a diffraction grating is and have probably used it before in chemistry or physics class. But in case you forgot, I'll just describe it for you a little bit. It's a piece of film that has parallel lines etched into it, and it diffracts light into many different angles. Alright, so we had the laser, which was 1 meter from the board, and it created two secondary nodes, and we measured how far this secondary node was from the primary node, and it was 54.3 centimeters. So then what we'll do is we'll find this angle, and once we find that angle, then we will be able to find the wavelength of the laser. Alright, so we took the inverse tangent of 53.4 over 100, and we found that the angle is 28.5 degrees. Alright, so the equation that we want to use is d times the sine of theta is equal to m times the wavelength. And the diffraction grating that we used had 750 lines per millimeter. So to find d, we do 0.001 meters over 750, since we had 750 lines per millimeter. And that is equal to 1.333 times 10 to the negative 6. So an m is equal to 1 because the node that we are examining is in the first pair of secondary nodes. Alright, so it's 1.333 times 10 to the negative 6 times the sine of 28.5 over 1 is equal to the wavelength. And that is equal to 6.36 times 10 to the negative 7th meters. So 6.3 times 10 to the negative 7th meters is equal to 636 nanometers.
So now we're going to try to find the percent error of our calculations by doing the absolute value of experimental value minus accepted value over accepted value, and then multiply that by 100%. And then we found that it's actually 0.5%. One thing that we didn't mention earlier is the fact that there are many more nodes outside of these with larger angles, such as these two. And in order to find the angles, we need to plug in m for 2 in order to find the angle for these two. We found the angle by using the arc sine equals m times the wavelength over d, and using that we found that it was 73 degrees. Once we found the angle between the tertiary node and the primary node, we were able to find the distance between these two nodes, and we calculated it out and we found that it was 327 centimeters between the two.
All right, thanks for watching our Theoretical Thursday. Have a good one.
Bye-bye now.